Okay, crossing over to the next topic, we have regarding subspaces of Rn, and a subspace of Rn is any set H in Rn. It's going to have three properties. Okay, you're going to have the zero vector is going to be in H, and for each u and v in H, the sum u plus v is in H, and for each u that is in H, and each scalar c, the vector c times u is in H. And for what we will be looking into in this section will be what will be referred to as column and null spaces of matrix A. And we have, first of all, okay, we have within the subspaces, okay, we have the column space, and the column space of matrix A is going to be the denoted as COL A, and you're going to have the space, column space of matrix A to be the set of all linear combinations of the columns of A. And we have the column space of an m by n matrix is going to be a subspace of Rm. Okay, and again, m is being referenced to the number of rows. And again, just for the denotation, okay, you have COL A refers to the column space of A. And for a vector B to be in the column space of A, okay, we must have that AX is equal to B must be consistent. Okay, so we need a consistent system, okay, for a vector B to be in the column space of A. And just as a given example, okay, we have for our coefficient matrix A, okay, we have a 2 by 2 arrangement where we have for the first row we have the elements 1 and 3, bottom row we have 5 and 7, and we have for the given vector B, okay, we have again, we have the elements 2 and 9, and we have the determination of whether B is going to be in the column space of A. So we must determine if AX equals B is going to form a consistent system. So establishing what we have from this equation, if we express as an augmented matrix, okay, so we have running across, we have 1, 3, 2, and we have from A and B, we have also running across for the bottom row section, we have 5, 7, 9. And looking into what we have here to get this into reduced echelon form. Okay, so we have second row minus 5 times the first row elements. Okay, so the second row is converted to 0, -8, and -1. Okay, so we have 1 and 0, okay, for the first column, and I want to express this next column as 0 and 1. And I can start out converting the -8 into a +1, so I can take -1/8 of the second row. So we have in the rewrite, okay, we have 1, 3, 2 still at the top, bottom have 0, 1, and 1/8. Now I want to make the 3 into a 0, so we can go through the process of taking from the first row 3 times the second row elements, okay, and undergoing the process, we end up at 1, 0, 13/8, and 0, 1, and 1/8. And we have for our solution in X, okay, now the system is consistent. So the B is going to be in the column space of A, and you would have that X of 1 would be at 13/8, and X of 2 would be at 1/8. And again, we have a consistent system that has only one solution for X of 1 and X of 2. And again, because we do have consistency, okay, B is in the column space of A. Now, let's say that if we have for A and B, this time we have A again at 1, 3, 5, 7, and this time we have for B we have 6 and 14, and whether this vector is going to be in the column space of A. Okay, so again we're looking to see if AX equals B is going to be consistent. So looking at what we have upon establishing the augmented matrix, so we're starting out with 1, 3, 6 for the first row, and the second last row we have 5, 7, and 14. And again, just going from 5 to 0, taking 5 times the first row elements away from the second row elements. Okay, so we have in the next step we have 1, 3, 6 again, and bottom row we have 0, -8, -16. So a bit of deja vu. Again, we have -8 converted to +1 upon taking -1/8 of the second row. So we have 0, 1, 2 at the bottom, and again we have with the middle column 3, converting that to 0. So again, we're going to take the first row and deduct 3 times the second row elements. So we end up at 1, 0, 0, and 0, 1, 2. And again, we have a consistent system with x of 1 at 0 and x of 2 equal to 2. So again, this vector b is also in the column space of A. And now let's say that if we're going from 2 by 2 to 3 by 3 matrices for A. Okay, so we have A at 1, 3, 0, 5, 7, 0, 3, 4, 1. And we have with B, we have 2, 10, and 6. And to determine whether this vector is going to be in the column space of A, so again, we have AX is equal to B. And for what we're going to have here with the augmented matrix that is formed, again, we have 1, 3, 0, 2, 5, 7, 0, 10, and 3, 4, 1, and 6. And to get the 5 and the 3 converted to 0, again, we have R2 minus 5 times R1. And then we have R3 minus 3 times R1. So we have these numbers, and again, from the second row, negative 8 is in the next pivot position. And if I convert this into a positive 1, so I'm going to take negative 1/8 of the second row. So I have going across in the middle, I have 0, 1, 0, 0. And so we have for the first column, I have 1, 0, 0. And I want for the next column, I want 0, 1, and 0. So converting the 3 and the negative 5 to zeros. First row, I'm going to deduct 3 times the second row elements. For the third row, I'm going to add 5 times the second row elements. So we end up with 1, 0, 0, 2, 0, 1, 0, 0, and 0, 0, 1, and 0. So we have another consistent system where we have x of 1 at 2, x of 2 at 0, and x of 3 also at 0. So this vector b is in this column space of A. And if we take another example, and we'll say that we have for A, we will have this at negative 3, negative 2, 0, 0, 2, negative 6, and 6, 3, and 3. And we had that B is going to be at 1, 14, and negative 8. And taking AX equal to B and writing in augmented matrix form. Okay, now what you're going to have ultimately is that upon going through all the steps involved, taking negative 1/3 of the first row, and then after that, taking the third row and deducting 6 times the first row elements that are formed, and then following through, taking half of the second row elements, and then finally getting to the reduced echelon form. Okay, we have, again, first row minus 2/3 of the second row elements, and then we have the third row elements adding the second row elements. And what you have here, now we got 1, 0, 2, negative 5, 0, 1, negative 3, 7. Okay, but we do not have the third pivot position. What we have instead, okay, we were trying to say that 0 is equal to 1, which is not true. The system is inconsistent, so we have for this particular vector b, 1, 14, and negative 8 is not going to be in the column space of A. All right, now, and let's say that for what we have in the next go-round, going from column to null spaces. Now we have the null space of an m by n matrix. It's going to be a subspace of Rn. And it says equivalently, the set of all solutions of a system AX is equal to 0 of m homogeneous linear equations and n unknowns is a subspace of Rn. And we'll be looking at some samples and also looking at a couple of items where we will be looking at establishing a basis for a subspace H of Rn. And now, and let's say that for what we have regarding null spaces. And let's say we have A as a 2 by 2 matrix. So we'll say we have negative 1, 2, 3, and 4. And we have vector U at 3 and 4. And it says to determine if U is in the null space of A. So for this to be possible, the product of A and U must be equal to 0. So if I multiply A and U together, okay, so we have, so treating the elements from U almost like weight, so you have 3 times first column from A, and you have plus 4 times the second column values from A. And what happens here is that we have negative 3 plus 8 is 5, 9 plus 16 is 25, which is going to be non-zero in value. So in this particular case, because the product does not equal to 0, U is not in the null space of A. Now, if we look at the next go round, And say we have given A is equal to -2, -1, 3, 4, -5, 2, -4, 2. And we had that U is equal to the vector, which will consist of the elements 3, 4, and 5. Now again, if we are to determine whether U is in the null space of A, the product of A times U must be equal to 0. So for A times U, what we have in the setup, so we have 3 times -1, 3, and 2. And you have plus 4 times negative, let's make that 4 times 2, 4, and -4. And then we have plus 5 times the vector, which in this case, all right, we're going to have at -1, -5, and 2. And just do a modification here. So you have, so that has to be a -1. So looking at combining, so we have -3 plus 8 is 5, and then take away 5, we have 0. 3 times 3 is 9, 4 times 4 is 16, 9 plus 16 is 25, and then you have 5 times -5 is -25, 25 minus 25 is 0, and then for the bottom section, 3 times 2 is 6, 4 times -4 is -16, 6 minus 16 is -10, and 5 times 2 is +10, and negative and positive 10 add up to 0. If you notice, you had the top, middle, and bottom numbers in the resultant vector to be at 0, and since the product is equal to 0, it turns out that this vector U, the 3, 4, 5, is going to be in the null space of A in this particular case. All right, now for what we have in the case of forming a basis for the null space of a matrix. Okay, so and we have here, say we have a matrix A, so you have going column by column. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. And for finding out a basis, okay, we're looking at a set of values x such that A times x is equal to 0. And if we form an augmented matrix, okay, we have going from A to 0. Okay, so we have a 3 by 4 matrix. And to get this in terms of reduced echelon form, okay, so going through the process, so you have R2 minus 2 R1, R3 minus 3 times R1, and we have this step, and then taking, converting the next pivot position value from -3 to 1. I'm going to take -1/3 of the second row elements. Okay, so I have 0, 1, 2, 0 going across, and we have going all the way out to the reduced echelon form. Okay, so we have R1 minus 4 R2 and R3 plus 6 times R2. So we have 1, 0, -1, 0, 0, 1, 2, 0, and then we have consistency with 0 equal to 0. So we have x of 1 minus x of 3 is equal to 0. X of 2 plus 2 times x of 3 is equal to 0. And for what we have here, x of 1 is equal to x of 3. X of 2 is going to be equal to -2 times x of 3, and x of 3 is a free variable. So we have in the solution, we have x of 1, x of 2, x of 3 equal to ultimately x of 3, where we have times the vector 1, -2, 1, and just a little shorthand, a little bit of coding here. You have U to represent this 3 by 1 vector, so we have equal to x of 3 times U. So we have this U, that is 1, -2, 1. You can either write as in set symbol terminology or as a vector. So we had this to be a basis for the null space of A. And if you have, say if I were to add a column for A with 10, 11, and 12. Okay, so if I'm looking for what I have in terms of a basis, okay, for the null space of this vector A, what's going to happen here is that what you're going to have going through the processes, very much the same steps, and we have with the solutions. Okay, now you'll have x of 1 equal to x of 3 plus 2 times x of 4, x of 2 equal to -2x of 3 minus 3 times x of 4, with x of 3 and x of 4 as free variables. And just for the breakup here, okay, so we have with x, okay, this will come down to x of 3 plus 2 times x of 4 from x of 1. From x of 2, I have -2 times x of 3 minus 3 times x of 4. X of 3 is equal to itself. X of 4 is equal to itself. And we have, just for the solutions, we have u and v representing what we have for x of 3 and x of 4 are free variables. And so we have, with the combinations here, the set consisting of u and v is going to be a basis for this null.